and the heat transfer. We'll also discuss in the calorimetries, where we can expect some 2 to 3 questions from this particular thing. Okay, so first one is I'm going to just discuss the basic things of the thermal expansions and different types of the thermal expansions and in the different scenarios. Next one is in calorimetry and the thermal radiation and Newton's laws of cooling. So these are the things which have been asking in the examination. So first we'll start with the thermal expansion. So before going exactly to the thermal expansions, we'll be seeing that the thing is called as an the temperature and the heat, different methods of measuring the temperatures and all these things, please. So what do you mean by temperature here? So temperature means it is a measure of or degree of hotness or coldness of a body. So this is the degree of hotness or coldness of a body, which is nothing but called as a temperature. So generally, how do we measure this one in terms of the degree centigrade, or you can go for an Kelvin statement, Kelvin scales, or Fahrenheit scales like that. So I'm going for the general conversion relationship, that is for the degree centigrade, that is C by 5 is equal to, this is F minus 32 by 9. So it is a conversion from degrees centigrade to degrees Fahrenheit, or this can be written as, and this is 9C is equal to 5F minus 160. So if I want to take the C on the y-axis, then I can take in this way, that is 5 by 9 into F minus 160 by 9. So the shape of the graph for this one is going to be an, so it's a negative intercept that we are going to get it. So where the slope will be positive and intercept point is going to be the negative one. Suppose this is your C on the y-axis here, and this is your on the x-axis. If it is degrees Fahrenheit, then the shape of the graph will be like this. It's going to be intercepting at this particular point. This is going to be the 160 by 9. It's a straight line which is intersecting at this particular instant. And your slope, that is your tan theta, can be written as, and this is equal to the 5 by 9. The same thing can also be turned in the F. You can take that on the y-axis and you can write the C on the x-axis also. Or if you want to convert from one scale to the another scale, except from the degree centigrade to the Kelvin scale, so you can take it as a scale 1 minus or scale minus lower fixed point by upper fixed point of that scale minus lower fixed point of the scale. This always remains constant. Okay, so using this particular relation, we can determine this particular thing, or we can find, you can convert from one scale to the another scale. So why does this particular now coming back to the exactly the thermal expansion thing? So why does this particular expansion will be takes place? And expansion will be taking place in the solids, liquids, and as well as gases. So coming to this expansion, expansion will be taking place in the solids, liquids, and gases. So first we'll be dealing with an expansion in solids. So what is this expansion in the solids case, please? So as you rise the heat, that means as you give the heat to any particular solid, that means you are rising the temperature. So since you are rising the temperature, So what will happen? They are going to by supplying the heat, you are rising the temperature. That means you are giving some energy to this one. So because of that one, the due to the thermal agitations, the molecules will be oscillating about there, or their point of oscillation will be shifted, and so that they will be changing, their expansions are going to be taking place. And coming to the expansions of the solid, you do have the three types of the expansions. There are three types of expansions. So first one is called as a linear expansion. Second one is an aerial expansion. And the third one is an volume expansion. So in the linear expansion, suppose the Y sort of a things or rod sort of a things. If they expand, so they are going to be undergoing the linear expansions case. Linear expansions. That means if any particular object which is having a considerable length and negligible area of cross section. So linear expansions, the coefficient of linear expansion is being represented by, suppose that means this is sort of a rod or a wire sort of a thing. So this is your initial length L. Now, due to the heat, whatever the rise in heat supplied, and there is an rise in temperature, it is been expanding by your delta L. So you are rising the temperature from T1 to T2. We are rising it. So due to that, that expansion is been taking place, or your delta T, you can consider it to be the T1 minus, sorry, T2 minus T1. So now the change in the length will be the delta L is equal to, or delta L will be equal to the proportional to the initial length into delta T, or the change in the length as you are going to increase, or your change in the length delta L is equal to alpha into, or L into alpha into delta T, where alpha is called as a coefficient of linear expansion. So the new length is going to be the, or L final, or L2 or L dash is equal to L plus, you can take it as a delta L, or this is L plus delta L is L alpha delta T, or you can write it as an L of 1 plus alpha into delta T. So from this relation, you can find out in the different situations, that is delta L change in the length can be equal to the L alpha delta T, and whereas delta L by L, from this one it is used to the percentage conditions, that is alpha into delta T. So like this, you can apply for the different situations. And the second type of the expansion is called as an aerial expansion. Aerial expansion is also called as an superficial expansion. So this is, and the coefficient of the superficial expansion is being represented as an beta, or else if you take any particular area sort of a thing, if on rising the temperature from T1 to T2, so the area is going to be increasing like this. Only there is an increase in the area, its length and breadth, both of them are been increasing. That the initial area is going to be the L into B, and your final area or A2 can be written as an change in the length, that is L dash into B dash. Your L dash is L into 1 plus alpha into delta T, and another one into B dash can be written as a breadth B into 1 plus alpha into delta T. So on solving this one, you can write it as an A2 can be written as a, it is A into 1 plus alpha into delta t whole square. Or we're going for the binomial expansion, so taking the first two terms into the consideration, since alpha into delta t is a very small value, 1 plus x to the power of n can be written as an 1 plus nx. So using this particular thing, a can be written as an or a1 into this will be the 1 plus 2 alpha into delta t, and this 2 alpha can be written as an 1 plus beta into delta t, where alpha is equal to, or 2 alpha is nothing but your beta, where beta is called as a coefficient of areal expansion. So there are the different applications will be there, and the last one is called as an volume expansion. So coming to this volume expansion case, please. So what is this volume expansion condition or a cubical expansion? You can also call it as an. In this one, the shape or the volume of the thing is going to be increased. Or in the similar case, V1, if I write it as an L into B into H, by solving in the same procedure, you can get it as an V2 is equal to V1 of, and it will be written as an 1 plus gamma into delta T, where gamma is equal to 3 alpha, and the relation between the suppose if I write this one in terms of the beta, this will be the 3 beta by 2. So this is how you can have the relationship between the alpha beta and this one, and from the volume you can derive the change in the densities with rise in the temperature, that is change in density with mm, temperature. So this is another important relationship. This you can write it as a density or rho 2 is equal to rho 1 into 1 minus gamma into delta t. This is a came under the binomial conditions, or the general formula you can take it as a rho 2 is equal to, or rho at that particular temperature is equal to 0 degrees by 1 plus gamma into delta t. So you have got the relationship also here, please. Now, in the different applications, you can use this coefficient of linear expansions and all these things. For example, if I go for thermal stress. So in this thermal stress, suppose a rod is being fixed between the two rigid supports here. So let these are your fixed and rigid supports. Now we are raising the temperature from T1 to T2. Then T1 degrees centigrade to the T2 degrees centigrade we are rising. There is not enough space for the rod to expand. So it will apply the force on this particular fixed thing. And that thermal force from the elasticity can be written as an stress is equal to, that is force by area, is equal to you can put it as an y into E by L, that is the elongation by Young's modulus by elongation into original. Or this is Young's modulus into delta L by L. E is nothing but an replace the delta L by L. Then thermal stress F by A can be written as an y into alpha into delta T. Or thermal force can be written as an it is y A alpha into delta T. So similarly, you can also take it for an pendulum cases. So suppose the length of the pendulum, or if it is a pendulum is been suspended by a string, metal string conditions. So in some situations, what will happen in the summer or in the they'll be try to expand. If the length is going to be expanded, time period will also increases. So on that sense, we know that time period of a simple pendulum is going to be the so time period capital T is equal to the 2 pi into root over L by G. So from this one, we can say that T is proportional to the square root of the length, or delta T by T can be written as an half into delta L by L, that is change in the length by original length. Now we can substitute this delta L by L as an alpha into delta half alpha delta theta, where theta is nothing but your temperature rise, change in temperature. Delta theta is called as a change in temperature. Okay, so this is the situation. Next one. So coming to in this one, so coming to the calorimetry case, please. Uh, Calorimetry actually it is not, it works on the principle of only one principle is there, that is heat lost by the hot body is equal to heat gained by the heat gained by cold body. So there is a transfer of the heat will be taking place between the two bodies. Okay, so it will transfer of the heat will be taking place over there between the two bodies. One is going to be the hot, and another one is going to be the cold body. Obviously, we know that heat will be transferred from the hot body and it can be absorbed by the cold body. So what will happen here? So whenever the heat is being supplied to any particular body or any particular substance, uh, so what will happen here? So when you supply the heat to any particular substance like this, it can be utilized in two different ways. One is it can rise the temperature. Okay, so there will be the rise in the temperature can be taking place. On second case is then change in the phase. Change in phase. That means from solid state to the liquid state or liquid state to the gaseous state. Change in the phase, nothing but melting. And another one is going to be the vaporization. Another type is nothing but an sublimation. So these things can be happening. So when there is a change here, heat will be written as an that is M into L, where L is called as an latent heat. So your latent heat of the fusion is going to be the 80 calorie per gram, and latent heat of vaporization is 540 calorie per gram. So these are the things, please. And for rising the temperature, you can rise it as an heat supplied Q is equal to that is Ms into delta T. So this is the heat supplied in this case. Okay, where S is called as an specific heat. So for the different substances, specific heat will be defined, or specific heat can be defined as an specific heat is equal. That is S is equal to 1 by m into this is dq by dt. The same thing will be written in terms of the definition, that is amount of the heat required to rise the temperature of a 1 kg of a gas by 1 degree centigrade. So this is your specific heat case, please. So it is a very small, that is for 1 degree rise in temperature, how much heat we need to supply. And there is another term called as an heat capacity. So heat capacity, what is this heat capacity is going to be the either represented by the H or C, anything like this. Heat capacity C is equal to this is simply dq by dt. And the relation between the heat capacity and this one and the specific heat is C is equal to ms. So this is thermal capacity or the heat capacity or anything. This is equal to the mass into specific heat. Thermal capacity. These two are the same things, please. Fine. So next is another one. There is a term called as an water equivalent. The water equivalent is also equal to your ms only. So next, if we go for this one, in this case, mechanical equivalent of the heat means mechanical e- equivalent of heat. So what is this mechanical equivalent of the heat is nothing but an it is an whatever that work done is going to be the heat supplied and the work done relationship. In this case, these work done W is equal to it is JQ joules mechanical equivalent of the heat, where J is called as in joules mechanical equivalent of heat. For 4.187, it is joule per calorie. So which is used for the conversion factor or generally for the calculation purpose, you can go for the 4.2 joule per calorie. So if I just round it to the after decimal first digit. So this will be used to convert from the one state to the that is the calories to the on another state. So these are the things please. We can go for a simple examples in the calorimetry. In the sense, for example, what sort of a question? Suppose 5 grams of ice is being mixed. Ice at some minus 10 degrees centigrade is mixed with same 5 grams of water at some 20 degrees centigrade. Now, obviously, in this case, the water is at a higher temperature and this is the cold temperature. So the water is the one which is going to be the giving the heat. That means heat lost by the hot body. The maximum heat that it can lose is going to be the ms delta T, and the specific heat of this one is going water is going to be the one 5 grams into specific heat 1 into change in temperature 20 degrees. It will be the 100 calories of the heat is being it can give. So who is going to take this heat? The ice is going to take this heat, and with this 100 calories, what does an ice will do? So ice will first two parts. There is a two chances of it. First part, it can come down to the minus 10 degrees to the 0 degrees. For that one, how much you need? M into specific heat of the ice. This is specific heat of the water into delta T. Mass is 5 grams. Specific heat of the ice is 0.5 into this one is going to change in temperature 10 degrees. So on the sense that is 25 calories is being used to convert the ice from minus 10 degrees to the minus 10 degrees ice to 0 degrees centigrade of ice. Now, out of the 125 gone, so with the remaining 75, what it will be do? That is the Qg1 and Qg2 is equal to 5 grams of the ice is there. So now it is only taking the 75 grams is been left over. That is 75 calories is equal to m into which is not sufficient to completely melt it. So ml is nothing but and this is 80. So m is equal to 75 by 80. So this amount of the mass is only melted and it is still in the shape of the ice only. So mass of the ice which is melted, this is the case. So since the total whatever the leftover energy is there, it is not sufficient to completely melt it. So it cannot rise the temperature. So resultant temperature will be resultant temperature will be equal to the maintain at 0 degrees centigrade. So since because it is not even completely utilized to convert it, okay, so it can also be it can never increase the or it can never rise the temperature. There is no sufficient energy for it. Now, when we'll see one of the example of an this Joule's mechanical equivalent of heat. So let us take an heater is there. Suppose a heater is there. Okay, so can uh, generate heat generate heat up to 85,500 kilocalorie per hour. Let us take like this. Okay, now so now we need to rise the temperature? Then the amount of water, then the amount of water uh, whose temperature is rise from, whose temperature changes from some 10 degrees and 10 degrees centigrade to, okay, let me take it as and some 50 degrees centigrade. Okay, no, so now the corresponding specific heat of the water can be written as, and it is 1 calorie per gram. Now, when you convert it into the SI system, it is 4,200 joule per kg Kelvin. It will come. Now, so you need to rise the temperature by from 10 degrees to the 50 degrees. We have to change it. For that one, heat Q is equal to, that is EMS delta T. So heat supplied, your mass is the unknown factor here. That is M into specific heat is equal to 4,200. And you need to rise the temperature by 10 to 50, in the sense it is 40. So the total heat supplied is going to be how much? But the total heat is in the form of the kilocalories here. That means 85,000 into kilocalories means 10 power 3 into 4.2. I'm taking for the calories to convert into this one. Okay, so now in the by kilocalories per hour. So this should be equal to the M into 4,200 into this is 40. So now this should be most comfortable. You can solve this one to find out the how much mass is being, the amount of the water whose temperature is been raised in this particular instance. So these are the important cases, please. So please be careful of this one. Now coming to the another topic, which is called as an thermal radiation or the heat transfers. So thermal radiations are going to be the another very important, which comes under the heat transfer chapter. So heat can be transferred in the three different ways. One is called as in conduction. Second one is called as an convection, and third one is radiation. So in these three ways, the heat can be transferred. So basically, first I'll just go for the conduction thing. What is your conduction? The heat will be transferred from one body to the another body if there is any physical contact. So that is heat is going to be transfer, rate of heat transfer dq by dt is proportional to the area of contact, so proportional to the temperature difference, and inversely proportional to the thickness or the length through which heat is being transferring, L. So on this one, you can write it as an dq by dt is equal to Ka delta theta by L. So this is your rate of heat flow in the case of conduction, please. So where K is called as a coefficient of thermal conductivity, coefficient of thermal conductivity. So this is the very important thing, sir, coefficient of thermal conductivity. Next, I'll directly go to this radiation. So what is this radiation? Heat is going to be transferred in the form of an electromagnetic radiation or electromagnetic waves with a speed of different velocities will be there, 3 into 10 to the power of 8 meter per second, got a different wavelengths. So in this radiation, the major important terms that we need to discuss over here is the Stephen's laws conditions, that is the rate of heat transfer, and the Newton's laws of cooling and the Stephen's Boltzmann's law. All these things we can discuss here. So coming to the radiation according to the Stephen's law here. So what is the Stephen's law? The energy radiated so per unit area per second is going to be directly proportional to the absolute fourth power of absolute temperature. So that is called as your Stephen's constant. Fine. So let me write this one. Stephen's constant is or Stephen's law is equal to so energy radiated per unit area per second is proportional to fourth power of absolute temperature. Okay, so this is the one basically. That means energy by area into time, which is nothing but this is called as I, and you can say that I as an intensity. Intensity is equal to sigma into T power 4, or I can also go for an emissivity or these things. So from this one, E by T is equal to sigma A T power 4, where E by T can be written as and this is power, and E by T is the E by T. I'm just expanding this as an E by T is equal to rate of heat, that is dq by dt heat conditions sigma A T power 4. So now sigma A T power 4 dq by dt, dq can be in the different formats. It can be ms delta T or it can be ml. So if it is an ms into delta T by delta theta or delta capital T by delta small dt or delta small t time is equal to sigma A T to the power of 4. So from this one, that is a decrease in the temperature, d delta capital T by delta small t is equal to sigma into area by this is specific heat into T to the power of 4. So this is another important relationship. This is, you can say it as a rate of decrease conditions. So this is called as your Stephen's law. So for this particular Stephen's law, Boltzmann has been just changed a small variation. He has given a small sort of a variation to this one. So that is called as an Stephen's Boltzmann's law. So according to the Stevens-Boltzmann law, the rate of cooling or the decrease in the temperature of the body not only depends upon the body temperature but also surrounding temperature, that is E by A into T is equal to sigma T to the power of 4 minus Ts to the power of 4. So from this one intensity, this is nothing but your intensity. So from this one power is equal to, which is E by T is equal to sigma A into T to the power of 4 minus Ts to the power of 4. So this is your Stephens-Boltzmann's relationship. Or the same thing from here, you can write it as an d temperature, d theta by d small t can be written as an emissivity E A into sigma by, this is going to be the ms, which is t to the power of 4 minus ts to the power of 4. So this is, that means according to the Boltzmann has enhanced the Stephens law that the decrease in the temperature not only depends upon the body but it also depends upon the surrounding temperature. Okay, so this is the one of the things, please. From this one, the rate of cooling or the decrease in the temperature can be obtained here. So that is the rate of cooling, whatever is going to be the, which is called as a Newton's law of cooling. So now this will be discussing later. So now in this case, this is one of the situation, and there is another law for the radiation which is also very important. That is Wein's law. According to the Wein's law, what is the relation, sir? The minimum wavelength of any object is going to be inversely proportional to the temperature, and that proportionality constant is equal to B by T, where B is called as an Wein's constant. So B is called as a Wein's constant in the sense it is 2.8 into 10 to the power of minus 3. So these are your different cases till now. So Wein's law one is the Boltzmann's law. So we need to majorly discuss about the Newton's laws of cooling thing. That is the last we need to go for this one. So what is this Newton's laws of cooling? So when a body, what will happen? When a body radiates, what will happen? Radiates heat because it is giving out the heat. What will happen? To the surroundings. To the surroundings, then what will happen? Then temperature uh, of the body of the body cools. So how does this particular thing will happen? So we'll see in this case, that is according to the Stephens Boltzmann law, d capital T by d small t, that is the change in temperature is equal to, it will be, since it is in the decrease, minus E A yes by, this is ms into t to the power of 4 minus ts to the power of 4. T to the power of 4 minus ts to the power of 4 conditions. From this one, if I take it as a d capital D by t to the power of 4 minus ts to the power of 4, if I integrate this one, is equal to sigma minus A into E by, this is equal to the ms integral of time, that is 0 to t seconds. Here it is left with some temperatures T1 to T2. On integrating this one, you can get this as an integrating and solving this one obviously. So you should be getting it as a d capital D by d small t is equal to minus 4e into k into, that is Stephens Boltzmann law, ke Stephens Boltzmann law into emissivity into area by denominator is going to be the same ms into temperature changing from T minus Ts surrounding temperature. So rate of cooling d capital T by d small t is proportional to the T minus Ts, where T is nothing but an average value of this one, that is T is equal to T1 plus T2 by 2, and this is T in a given time interval. What is the difference in the time periods? So that is a major thing, sir. So this is called as a Newton's laws of cooling relationship, please. This will be used in the different circumstances, or from here also you can use this relation from here. He might be asking you the graphical things or different sort of a things, sir. So you should be careful in this particular thing. So that is according to the Newton's laws of cooling, how you can write d capital T by d small t is equal to some constant k into, this is T minus Ts. If I rearrange it, this one d capital T by T minus Ts is equal to k times of the dt. This is nothing but an integrating of this one. This will be converted as an ln of T minus, this is Ts. Limits have been changing from the T1 to T2, which is equal to the K into T1 minus T2 conditions, please. So this is the T2 minus K into temperature conditions, that is KT. Now if I substitute in this one, this will be the ln of how much? First term will be the T2 minus Ts minus ln of T1 minus Ts is equal to KT, with a negative sign obviously will be flowing over there. So from here, after substitute, this will be the ln of T2 minus T1 by T1 minus Ts is equal to minus K into T. So ln is equal to e to the power. This will be the T2 minus Ts by T1 minus Ts is equal to e to the power of minus kt. Or on solving this one, I can get the T2 minus Ts is equal to T1 minus Ts into e to the power of minus kt, or T2 is equal to T2 is equal to temperature of the surroundings plus T1 minus T2 into e to the power of minus kt. So this is how you can get the Newton's laws of cooling relationships. And when you plot a graph between these two things, or log of this particular thing and the time, then also you can get it's a straight line passing, it's a negative slope, minus sign will be there here. So please be careful of this one. He can ask you in any different formats, please. Fine. So now this ends up our today's session. So all the best to each and everyone who is been attending this particular class or listening. So all the best for your NEET program. So by this particular junction, I am closing.